I will truncate it at about 40 minutes, so the last 20 minutes are for Jacques, with whom I've collaborated on another project. So my talk of today and of IPP Berlin was on designing twisty puzzles. Many of you know that I have an interesting hobby. So what I will talk about today is, first of all, I'll give you some references, where to find more information, what are the nice sites to watch, etc. Oh, I should have included Tony's site. Tony, please accept my apologies for that. Then I'll tell about the basic design. So what's the thing that twisty puzzle designers do in CAD to make a puzzle work, to design it. And then I'll go through a whole lot of specials. I'm not sure whether I have enough time to go through all of them, but this list is far from complete, so there's even much more. So let's start with the references. First of all, what's a twisty puzzle? Well, it's fairly obvious to all of us, but Jerry Slocum has a formal definition which is called sequential movement rotating cube type, and there's even more definition behind it. There's also a competing categorization by Delgety Horder, and they call it sequential movement, sliding, shunting, etc. And the layman's definition is, of course, hey, that looks like a Rubik's Cube. So the first reference for twisty puzzles, I believe that almost all of you know it, is the Twisty Puzzles forum. It was founded by Wayne Johnson in 1999, and since then it's managed by Sandy Thompson. The problem was that the forum was getting too popular, it was taking too much capacity, and Sandy is now financing the maintenance of the forum by selling some puzzles through his web shop over there. So it's a big website. It has more than 2,000 subscribers, 20,000 topics, and several hundred thousand of posts. And it's a place where many of us share ideas, share new builds, work together as well. So to my perception, 2010 was really the golden year of twisty puzzles. In one single year, almost 700 new twisty puzzles have been posted at the forum. And as you can see from the daily visits, this is a statistic that I got from Sandy Thompson, you see that the forum has been really growing very fast. So another site really recommended, is Jaap Scherphuis in the room? No, he's not in the room, but he is in the building. Jaap Scherphuis, he developed a tool that's called Jaap Sphere, and what it does, it's you can select geometries. So this is the icosahedral geometry, and then with the slider you can make circles larger and smaller, and it gives you really a 3D feeling of a specific geometry. And the reason why this is very useful as a tool for twisty puzzle designers is that many times you have to design twisty puzzles layer by layer, and each of those layers you can model like this, and you can sort of imagine that, well, you see this big circle, that you can turn the circle and that then other things go in place, etc. Well, so this is a perfect visualization tool, and it's also a tool for inspiration. By just combining, mixing and matching, sometimes people discover, hey, this is possible as well. Gelatin Brain by Paul Smits is also a highly recommended site. It has hundreds of well, Rubik's Cube types of puzzles that you can really play in 3D, of course, on your computer screen. So when you have one of these and you click on these arrows, or I forget you drag, you can scramble and you can solve the puzzles. And some of the Twisty Puzzles fans, they really try to get better in solving puzzles that are on Gelatin Brain, and you can have high scores, etc. So one of the things that is very nice to know is that he has a lot of twisty puzzles that do not yet exist in reality. So sometimes you see discussions on the Twisty Puzzles forums like, please can somebody make a physical version of Gelatin Brain 1.1.74 or whatever the number scheme is? Another very useful resource in Twisty puzzles is Shapebase. Shapebase is a company that is actually from Eindhoven. They are about 5 kilometers from here. They have their own 3D printers, and they also have a collaboration with a lot of other 3D printing companies. So what they have is the website. The designer can upload the design, and someone else can buy the design or can buy the puzzle, and once it's bought, then Shapebase uses either its own 3D printers or a 3D printer of a partner company to make the puzzle. So Shapebase has a quite active puzzle community. Puzzles are added on a daily basis. So if you go to this hyperlink and you just browse around, there are hundreds and hundreds of puzzles of many types, including Twisty puzzles. And this is an example. It's the offset cube. I believe it's by Tom van der Zande. So, going to the basic design of a Twisty puzzle. How do you design a Twisty puzzle? How do you design any of, well, these types of things? Well, this is the basic recipe. Step 1, that's the creative part. Design the shape, design the cut curves. So, I'm taking this for an example. You think, well, what can I do? Pentagons, so that's the outside shape. And then the cut. What you have in here, it's not just, it locks together, so it has all kinds of steps going in. That's best illustrated with the Rubik's Cube. For a Rubik's Cube, the original Rubik's Cube has a very basic cut line. It's just a straight line, a straight line, straight line. And then that's all that's needed to design the Rubik's Cube. The next step is revolve this curve. So when you have this curve, you have in any decent cut program, computer-aided design program, you can make a revolution, and then you get these types of shapes. Then you do Boolean intersections, and then you get a piece that looks like this, and everybody recognizes that's an edge of a Rubik's Cube. And these steps for drawing a Rubik's Cube, some people can do that within a minute. So it's really not very much work. And then after that, it's just more work. You need to offset some of the faces to make sure that there is enough room for the pieces to move. You have to round the edges, because otherwise they are sharp and it doesn't turn that well. You have to make it hollow, because the 3D printed cost you pay per kilo printed powder. So if you make it hollow, you save money. And finally, you need to convert it to a language that 3D printers understand. Well, that language is called STL, so you have to convert to an STL, and that is also something that's not fully automated. It takes some cleaning up, some work to get it right. So this whole process has been perfectly explained by Ethan Scher, so I highly recommend this YouTube video, where in high speed he explains this in many details, and he also shows an example how a puzzle was made. So one other ingredient of the Twisty puzzle design, that's the shells method. I just showed you the curves for the Rubik's Cubes, which were just straight lines. Well, during the last decade, we have learned that straight lines are not the best and most effective way of designing Twisty puzzles. In order to make something stable and robust, what you need is straight lines that go to the center of your Twisty puzzle, and arcs that are part of a circle that go around that center. And this shells mechanism, it was already proposed by Bram Cohen in April 2004, but it was most effectively used by Panagiotis Verdes for his V-Cube design. And if you look at the V-Cube, you see it's all, this is the cross-section that you find in the patent. You see it's all straight lines going to the center, or almost to the center, and circles that go around the center. So when you make the revolves, what you get is spherical and conical cuts. So also you need to know where to build tolerance, because if you don't have any clearance between faces, then things can jam. So these are the rules of the thumb. The exact numbers vary from designer to designer. I like my gaps a bit larger, Tom likes it a bit smaller. And well, but the first is zero tolerance, where pieces pull or slide together. So here I have an example of a Rubik's Cube, where this is the center and this is an edge. And you see the edge pulls outward. So this is a place where you really need to have zero tolerance, no play at all, to keep it tightly in place. The place where pieces hover, there you can have a gap, and actually it doesn't matter if you make it larger, but at least it should be something like 0.3 millimeters. So this is the edge again. You see it hovers over the sphere in the middle, and this is something that should be sufficiently large to prevent jamming here. You also see that for the centerpiece there's a little hover here, but it's much smaller than what you have here, to make sure that the edge pieces never get jammed. Finally, sometimes you have grooves, and there the idea is you have 0.2 millimeter at each side. So this piece pulls outward. So here we have again the zero tolerance, here we have the hovering, and here it's centered with the 0.2. So these are sort of rules of the thumb, and they usually work quite well. Next step is making all the pieces round, because when they are sharp edged, then they will hook into each other. So this really depends on the preference of the designer. If you want to have something that looks good, you make the edges perhaps a bit sharper. If you want to turn it smoothly, to make it turn smoothly, you make it rounder. So you could, for instance, use 2 millimeter at places where, at corners, like this. 1 millimeter at rims, so that's, well, you see this is the 2 millimeter, this is the 1 millimeter. I hope it makes sense to you. And well, the hollowing shapeways says your pieces should at least be 0.7 millimeter wall thickness, so that's what I'm using. And then I have a little air hole to trap powder to keep the weight of the pieces. And well, here are some parameters for turning your piece into the STL format that 3D printers understand, but that's more for the specialists. So now we have done 15 minutes about generics. The rest of my time I will use on specials. So what are the new thoughts, new ideas that have happened the last 2 years in the Twisty puzzle design? Well, let's start with something. Hey, this is a picture that Tony might recognize. That's shape modding. Well, Tony is our mod god, so he is the hero of the shape modding world. And what shape modding is you start with an existing puzzle, and you can chop off corners, you can add pieces, you can remodel the whole design, and sometimes even remodel its functionality. One of Tony's favorite, or my favorites of Tony's, is one where there is a, I believe it's a 4x4 that looks like it has a ball inside, and I think that really looks elegant, but it has been modded, I believe, was it from a 4x4? Exactly, well, that's one I particularly like, but there are many more examples, and other people that are involved in shape modding are Andreas Nordman, Klaus Weniger, but many others have made excellent shape mods. And yeah, the way of modding is limitless, like connecting, adding pieces, reshaping. The Fisher cube is Rubik's cube but reshaped. So another category of modding, well, it's not modding, it's, I would call it bandaging. And I'm looking for another of my puzzles to demonstrate. Yes, those are there. So the concept of bandaging is gluing pieces together. the most beautiful example of bandaging was done by Noah and Adam Cowan. They built the Nightmare Cube. That's the one that you see here. From the outside, it looks like a regular 2x2 Rubik's Cube. And when you turn it, well, it turns like a 2x2. But once you start scrambling it, you see that at the inside, the inner 3x3 has been bandaged. And that's very naughty, because once you get it scrambled, some of the moves, they are blocked. So I think Nightmare Cube is well chosen. By Adam Cowan was also the Handlebar Cube. I made a 4x4 version of this. So this is bandaging of pieces together that are not adjacent. Andreas Nordman, he is making an overview of all the types of bandaged cubes that there are. And on the top right, you see all the bandaged cubes that exist. And he has just built all of them. I'm not sure whether he has solved all of them. Well, another bandaged puzzle, that's this puzzle, it's the Get Stuck Cube. It works like a Rubik's Cube. However, so in some directions it turns like a Rubik's Cube, but it has also sliding pieces. I hope you can see it. So each of them has a 3x3 sliding piece puzzle on top. And the bandaging here is that some of the sliding pieces are, well, combined. So this is a 1x2 sliding piece. And because of this piece, this rotation is locked. So I can't make this rotation, but I can make that rotation. And the whole idea of this puzzle is to get stuck. And that's so this puzzle is not yet stuck, because I can still make Rubik's Cube moves. But once you slide these bandages, there are a total of 6 of them. Each of them can bandage one slice of the Rubik's Cube. So when you have solved the puzzle, and it looks of course scrambled, but then you have a bandage going over every of the slices, and every rotation is stuck. So you have solved it when you get stuck. And this is, well, semantically something interesting. Another direction that people have been looking at is hollowing puzzles. This all started with Mr. Okamoto from Japan, who built the Void Cube. And in 2007, the Void Cube won the highest award from the International Puzzle Party design competition. It was awarded the Puzzle of the Year, which means that all the IPP participants thought that this was the best puzzle of the whole set, and also the jury thought that it was the best puzzle of the whole set. And that was very unanimous. And you see the puzzle, you all know it, it's a Rubik's Cube, it's hollow inside. But the idea of hollowing Rubik's Cubes, it has been extended. Uwe Meffert has made a hollow Megaminx designed by one of the people from our community. This is Tony Fisher's hollow cube, where you can look through this is the hollow Pentaminx, which has a really huge number of pieces. And well, this is the gift cube. Let me see. This is like it turns like a Rubik's Cube, but once you have solved it, it opens. It has hinges here, and you can see inside it's completely hollow. So it uses a dovetail type of mechanism, but once it's closed and you turn it, you can't open it. And the hinges that you see here, they act like bandages. So this move is now blocked because of the hinge. Another variation on the same theme, actually using almost the same mechanism as Okamoto, is the hollow cube. And as you can see, it's completely hollow in all directions, and still it moves like a regular Rubik's Cube. And extending this idea to a 4x4, it has inside a 2x2, which you can see shining to it, but outside there is a whole extra layer of pieces built around it. Another very nice concept was the idea of the circle cubes or the crazy cubes. It was Ale who started with this, but many people have expanded upon the idea that is to cut circles in Rubik's Cube. And the fun thing about these puzzles is that when you make a turn, then these outer 12 pieces, they will turn around, but the inner circle stays put. So it gives well, a quite new way of scrambling and solving. And I believe there are several circle cubes on tables to be played downstairs. One puzzle that I still haven't had in my hands and that I think is brilliant, and it's also like a singleton. It's only the one of its kind. It was the Chinese man Daking Bao who has invented it. It looks like a soccer ball, and at each pentagonal face there's a little metal loop. And what you can do is you can pull up the pentagonal face, and then the adjacent hexagons are pulled up as well. And then you can turn by multiples of 72 degrees, and then the springs pull back the piece in. You have a question?
No, just a comment. Crystal Blue has one downstairs.
Can I buy it?
I guess so, yes.
Oh, please. I really want to have this in my collection. I've been studying this from the photos, and it's a mechanism that's inside that is very different from what I've seen. And one of the things that surprises me is this mechanism is brilliant, but the whole community hasn't produced a second puzzle in this category for over a year. So, given the productivity of the community, this is really a rare and special item. So, thank you for the hint. By the way, you stay here for Sjaak, and then I'm running downstairs. Another thing that has happened are the higher order cubes. I already mentioned to you the Petamings, which is the Megamings with the pentagonal faces, but then 4 layers. Just 2 weeks ago, Matthew Banner presented to the Twisty puzzle community the Examings. So that's a Petamings with yet another layer, and it has something like 1,525 pieces. It's a huge number of pieces. We still have to see the video, but this is one of the directions people have been going to higher order cubes. And well, we all know that Verdus was the first person to break well, the high order limit of 5 by 5 by presenting a 6 by 6 and then a 7 by 7. And he made a patent that went all the way up to 11 by 11, which can now be commercially bought from one of the knockoff buyers in China, knockoff sellers. But it was Leslie Lee, also a person from China, who invented and built a Rubik's Cube of order 12, which is higher than the highest design of Verdus. And also the design that he used, it's not the Verdus design. So what you see here is a cross-section. This part is the center. This is the edge. You see the edge hangs at the center. Then these pieces hang from the edge, and these pieces hang again from these pieces. So it's a really brilliant and intricate design. It has also been patented. I don't think it's being mass-produced, but this is really quite inspirational. Now, I've taken up the challenge, as many of you know, to go to higher order Rubik's Cubes as well. I really have to thank Klaus Weniger and Shapebase, who have been sponsoring the first few prototypes. And as you may know, the first 2 prototypes were a big failure, also an expensive failures, and it was only the 3rd prototype that worked. So what's the challenge with building such a large puzzle? Well, the problem is stability. All these small pieces, they tend to tilt and to fall out. So the solution that I found is to the floating anchors technique, to have each piece have a very long anchor through the middle. So at the inside there is a 3 by 3. Let's see whether I have a photo of it. No, that's so at the inside there's a sort of spherical Rubik's Cube, a 3 by 3. So what you see here is the center. So this tiny centerpiece is actually the top of a very large piece that's in there. The corners are and the edges are hung from that center, and then all these other pieces are with their floating anchors. They are anchored to the puzzle, and well, I guess that many of you have seen this, and depending on your quality standards, this is something that actually moves reasonably smooth for something of this size. Of course, if you want to turn it in the other direction, it takes a bit of time to realign the parts. I could not round all the corners by 2 mm because then there would be no pieces left. The pieces themselves are 4 by 4 mm. So that's quite small. Going to another development that is in the area of gears. It was Bram Cohen from San Francisco who came up first with the idea of introducing gears in Twisty puzzles. And let's see whether I can find the Bram's cube. No, that's not the one. I'll show that this one as well. But it must be here somewhere. Anyway, so that was, well, it's the one that looks like this. So this has a total of 8 gears that are at the outside. Well, we have been working on several puzzles with gears at the inside. Many of you know the Meffert's gear cube. After that, the gear cube has the problem that if you make quarter turns, then the gears get stuck. But this is a variation that has, well, it's called the gear mix-up. When you make quarter turns, then all the gears realign again. And this is, I believe, the 3rd generation prototype, so it turns really smoothly, and you see how the gears change. So the problem for this puzzle is not only to get all pieces on the at the right place, but also in the right orientation. So we have done more things with gears. Here we have the Bram balls, where we have spherical pieces that are connected with each other through gears. Very recently, Uwe Meffert has brought to the market the gear shift puzzle, and this is one where you pull out the cube in 2 parts. Then the sides spin. Then you push them together. Then you pull them out in the other direction. And again, this was a collaboration by Bram Cohen and me. It was Bram who came up with the idea of having those 8 gears and having them turn always in groups of 4. And then it was me who designed the mechanism of this pull apart, push together, because if you pull it in one direction, you can't pull it in the other. And also I decided that it would be nice to have gears of different numbers. So this is this gear has 8 teeth, and this gear has 5 teeth. And for those of you who like the math, you can always get the gears fit if the number of teeth is a multiple of 3 different. So all gears have the same number of teeth that works, with for instance 10, 13, or 12, 15, or 12, 18, or 13, 19. All of those numbers work. So that's a nice calculation thing. The puzzle is not extremely hard to solve, but it's far from obvious. And I still have a few for sale downstairs. So, well, end of commercial. Let's go to the next one. That's the Polo Cube. Alex Polonsky is a guy that I know from Israel. I met him at the New York Toy Fair earlier this year, and he came to me with a prototype. I don't have it with me. That showed something that I hadn't seen before. It was sort of gears that engaged with each other, but disengaged as well. And I reused this mechanism for the Polo Cube. That's this one. And what you're seeing here is like in a gear cube. When I turn the sides, you see all the knobs spinning like that. But what makes it interesting is you see that these knobs are spinning in the same direction. But when I'm taking this one, you see that they are now turning in the opposite direction. So what we have inside is gears that sometimes engage and sometimes they don't engage. And again, this makes quite fun puzzle to play. One other that's in the gear area, that is the barbell cube. I call it, well, for the intellectual weightlifters. This one, it has a lot of gears inside. You see the photos over here. And with gears, the orange center is connected to the orange center. So if I turn this orange side, the other one will follow. Same for the blue side. Here's a blue center, there's a blue center. So they're connected. We have the red side here. So here we see the red center turn. Well, let's finish the demonstration. Here's yellow, and there we have, where's green? This is the green side, so this should be connected like that. At this moment, I don't think Klaus is in the room, but I'm working together with Klaus to see this still feels a bit too light. So we are now working on a metal version that is like 5 times as heavy. And if you have solved it, you really feel like you've done a workout. Another really exciting discovery of the last few years is the concept of jumbling. When Okamoto and Cowan independently discovered and built their first bevel cube or helicopter cube in 2007, they discovered that, okay, it was cubic, but when they make some turns, it made turns that change the shape from something that's not cubic. And it's really hard to explain, so I'll take you with this example, which was built later, also after a concept by Bram Cohen. And what you see is a shape that is sort of irregular. And once you make a turn, you see that sometimes turns at other faces are blocked. So even though I can make this turn from this position, I can't make that turn because it's blocked here. Of course, I could make this turn if I cut these pieces, so if I unbandage them. However, if I unbandage it and I make other turns, then I get into the same problem. So Bram Cohen made the definition of puzzles with that property: a twisty puzzle jumbles when it cannot be unbandaged into a doctrinaire puzzle. And he says, and you turn it into dust if you keep trying. So if you just keep chopping to unbandage, you can go on and on. Even though Okamoto and Cowan are known as the first discoverers of the concept of jumbling, it was actually David Pitcher who built his rhombic dodec in 2003. I believe he published it just 2 months ago. But this was the first jumbling puzzle that antedates the other one by several years. And as to show to how extreme you can go with jumbling, this is geometry with some pentagons. And even though I have designed it myself, I find it really hard to understand what is happening, what is disconnecting, and how to get it back in shape. Okay, many people had, once we knew that jumbling was there, many people discovered more jumbling puzzles. And at the Twisty Puzzle Forum, when a person makes a new design, very often the question is asked, does it jumble? And many puzzles turn out to be jumbling. And I hope that sometimes some person will try and do a PhD in this whole concept of jumbling, because I think there's enough material. One of the more exciting jumbling discoveries is the face-turning icosahedron, and I have one here. That's this puzzle. It's a logical extension of the rhombic dodecahedron, the megaminx, the Rubik's cube, the face-turning octahedron, and it was discovered by Matt Gala that it jumbles. And the funny thing is, both Jason Smith and Bob Hearn already had the face-turning icosahedron in their possession for half a year, but it was only after Matt Gala said, hey, your puzzle jumbles, they discovered that their nice puzzle, when they turn it, and okay, this is always a challenge, when they turn one face, not by the well-known multiples of 120 degrees, but something like this, that you can turn another face, and that you can keep on turning. So this is really a very strange way that is puzzle scrambles, and it's definitely not doctrinaire. Fudging. Another thing that I've been experimenting with, that is sort of doing things that are slightly illegal, hence the name illegal cube. What you see here is a Rubik's cube, but we have extended it such, well, you see big cracks between the pieces to make all the turns possible. And this type of turn should not be possible, but by fudging the shape a little bit, you can make them possible. And we do not have a formal definition of fudging, but anything that looks a bit funny may have been fudged. The fudmings is also an example of fudging. And here's another interesting thing that you see. This puzzle has been bolted from the inside out. And the good thing about it is because it has so many turning centers that you don't have to put caps on all these centers. So that's just one of the design techniques that I've been using. Deep cutting is another exciting development in our community. Jason's Pentultimate is the most extreme one. What is deep cutting? Deep cutting is when you have a geometric form, a twisty puzzle, and you cut it exactly in half. So for instance, a 2x2 Rubik's Cube is a deep cut puzzle. A 4x4 is a deep cut puzzle, but the 5x5 is not, because the cut doesn't go all the way to the center. Well, what Jason came up with was to try and deep cut a rhombic dodecahedron in this way, and the way he solved it is by really making a huge stack of pieces. Completely crazy, but I've tried it, it works. Since then, other people have improved on deep cutting. Tom van der Zande has built his mini Pentultimate. I believe he has it downstairs. And whereas the Pentultimate used to be an extreme puzzle, he found that just by using this cut line, so it's just 3 shells, and this is what the pieces look like. It's this size and it turns very smoothly. Still, it has a lot of hidden pieces inside, and I think it's well, a wonderful achievement and also wonderful collaboration and sharing of ideas with our community to get this far. So this is the Choposaurus. It was the Twisty Puzzle Forum, the Puzzle of the Year, voted by most people. And this piece has a total of 4 shells. You see how it starts. You start with an inner center and some edges. On top of those edges you build pieces, and you build pieces, and there on top of that you build another shell, and ultimately you end up with something that looks as elegant as the Choposaurus. Yet another interesting thing that happened, those are the hybrids. So combining ideas of twisty puzzles. So we all know the face turning octahedron, we also all know the corner turning octahedron, but this is actually one puzzle that does both. And it was Ethan Scher who came up with this one. But many other hybrids have been made where it's combining puzzle ideas. This one by Eric, where is he? Virgo, yes. By Eric Virgo. It combines some corner turning of the cube with a regular Rubik's Cube. It's really fun. Well, the final thing that I want to show you is the bubble sizing. This is something that was discovered by Anthony Villeveren, and his nickname is Boubless. It's something he's been called by his friend from his early childhood. And so, naming after him, we call this bubble sizing. And I have a few bubble-sized puzzles here. Now, let's immediately start with the most complex one, the bubble cube here on the right. And it's really hard to explain what bubble sizing is, but here you see, well, it's not completely cubic. What you see is this corner, this turn and this turn, they have only one piece in overlap. But when you have this one and that one, they have 2 pieces in overlap. So the fact that you have different relationships between adjacent corners, that's what makes this special. And I have one more, that is the Right, that's this one. Many of you know the mosaic cube by Mefferts. This one is sort of a mosaic cube, but it has here 3 little edges on a row. Here it has 4, and here it has 5. And when you make a turn, it always turns 3 at the same time. So here we have 3 at the same time, 3 at the same time. So again, this is a new geometry that we have just discovered this year and made the first puzzles. So as I mentioned, really exciting things have been happening in our community. I'm not going to the multi-core again, you can see that later. And I'm also not going to mention the Pettermings, the Royal Pentultimate, the Ulsing by our friends Ola Jansson, Pillowing, Floppy, and the list is much longer. So this ends my presentation. Thank you.